This is a quick review for the SOL. First, colligative properties. These can change the freezing point or the boiling point of a substance. In front of you see a container of water, it's liquid, and a container of sodium chloride aqueous. What's that mean? Well, sodium chloride is dissolved in water. So you have something and have ions in it right here. What this really is this is sodium ions that are dissolved, chlorine ions that are dissolved, and water. It's a liquid. In this, you just have water. It's a liquid. So, let's think about it. If I'm going to freeze water, water freezes at 0 degrees Celsius. Okay, so we'll talk about freezing point first. If I freeze water, think about the roads in the wintertime. What do? They put salt or sand on the road. If you're a water molecule and I'm a water molecule and we're trying to freeze, and someone puts a big blob of dirt in the middle of us, we can't freeze that well. Then, let's complicate matters. Let's add sodium and chlorine to the water, and all of a sudden, the water's attracted to the sodium and the chlorine. So therefore, it has a difficult time freezing. It freezes below. So it freezes at negative something, maybe negative 4 degrees. That helps you in the winter, doesn't it? It makes it so you don't slip and fall. All right. So colligative properties, if you put ions or something that dissolves in a solution, or make a solution, then you can actually lower the freezing point. Let's talk about boiling point. Have you heard of putting salt into water when you boil it, like you're going to make spaghetti? So I boil the water. It takes a long time to boil water. It boils at 100 degrees Celsius. Right now we're talking about boiling point. And I put salt in the water. The water tries to boil. It succeeds by itself, but all of a sudden you give me sodium and chlorine in the water. It complicates the issue. And so it boils higher. So it raises the boiling point, which makes it so that it takes longer for the water to boil, but your food cooks quicker. So let's look at what's going on. So here's water, and here's another water. This is what water looks like. It's bent, it's polar, okay? And actually what happens is the attractive force between one water molecule and another is called hydrogen bonding, right? Bad word, bonding. It's not really a bond. It's a very strong attractive force. Okay, bad word, bonding. It's not really a bond. This attraction between water molecules makes it so it freezes at 0, right? Has a hard time freezing. It has also a hard time boiling. Now, let's put sodium and chlorine into it. What do you have floating around here? You have an Na plus ion, which is going to attract to this negative oxygen. So this sodium ion attracts to water, and other water molecules come and surround it and dissolve it. Okay? Now, what's true here is this chlorine ion, which is negative, gets surrounded by all these H's. It dissolves. See? Okay. And so it dissolves, which makes water busy. It's busy being attracted to the sodium and the chlorine. And so it freezes below below 0, maybe at negative 4, and it boils above. So it's almost like in its busyness, it has a difficult time remembering to go, oh, wait a minute, I got to freeze because, hey, I really like this sodium and this chlorine. Or, hey, it's getting hot in here. Maybe I should boil, when indeed I'm attracted to that sodium and that chlorine. So, again, what happens? Freezing point is 0. Boiling point is 100. What happens if you put sodium chloride into it, make an aqueous solution, which is the sodium and chloride dissolved in water? It's going to lower the freezing point or raise the boiling point. Well, what happens if I put something like sugar in there? Are there any ions in there? It's a blob, right? This has got a sodium ion and a chlorine ion. This is just a blob. So it's going to lower it. It's going to get in the way, but not as much. So this lowers it more. What about this? There's sodium and chloride ions floating around here, right? This is just a blob. It's a covalent compound, so it doesn't form ions. So this also raises it, but not as much. This raises it more. That takes us right into electrolytes. Electrolytes are just that. It's something that lights a light bulb. So what lights a light bulb? Think about that. Electricity. So something that lights a light bulb, how convenient, has to have something that has electricity or the potential for it. So you need something that's aqueous, that has ions. And that means you have ionic compounds, acids, and bases. Those are usually the ticket when you're looking for something on the SOL. The ionic compounds have to have ions floating around. So if you look for a second, let's look at these choices. Sodium chloride is a solid block of salt. There are no ions. They're attracted to each other, so therefore this is not an electrolyte. What about aqueous? What's that mean? That means the sodium and the chlorine are floating around. So when you have aqueous ionic compounds, things that are dissolved in water, this right here is going to attract is going to light a light bulb. Well, that's good. Let's get the highlighter. This is going to light a light bulb. Sodium chloride aqueous. What's this kind of compound? Water. Well, there you go. That's one way to do it. That's not going to light a light bulb. There are no ions in water. What do we say about sugar back here? It dissolves as a blob, right? So, it dissolves as a blob here as well. And if you look at this, what's true? Where's carbon on your periodic table? Ooh, it's a nonmetal, so that makes this covalent. There are no ions. Therefore, guess what? This is also not going to light a light bulb. It's not an electrolyte. What about liquid salt? Still covalent, no ions. What about aqueous? Still covalent. So solid, aqueous, liquid, covalent compounds do not. They light a light bulb. What would be an example of acid? Well, what about, let's choose a pen. How about hydrochloric acid or sodium hydroxide? Those do light light bulbs. So aqueous ionic compounds and acids and bases light a light bulb. They conduct electricity. Equilibrium. You're used to seeing equations that have forward rates. So here's my reactants, and here's my products. Okay, in society, most of the time we use up our reactant to make our products. You buy the products at the store. You're not used to a reaction going in the opposite direction, but they can if it's in a closed container. Your lungs, your kidneys. So what's true at equilibrium? The sides are not equal. The forward rate is equal to the reverse rate. The rate of formation of a product is equal to the rate of breakdown of the product to make reactants, and they go back and forth. So it's not about sides being equal, it's about the rate. This is symbolized by the letter K. It's products over reactants. So you're going to go ahead and write NH3, which is a product, your only product. Put it in brackets, that means molarity, and the 2 coefficient becomes a 2 exponent. These arrows right here become the line in our fraction. And I'm going to go ahead and put H2, which I'll run into next, in brackets, and the 3 out front becomes an exponent. I'm not going to put plus, I'm going to times it. I'm going to put N2 down here. That's how you write an equilibrium expression. Writing it. Now what if I had values? What if they gave you a molarity for NH3? And they said at equilibrium, the molarity of NH3 is 2 molar. And at equilibrium, the molarity for H2 is 2 molar. And at equilibrium, the molarity for N2 is 1 molar. How would you solve for the equilibrium constant? Well, Won't you just plug these in? And this would become 2. And what would you do with it? Square it. And when you just take this and plug it in here, what would you do with it? Cube it. And what would you do with this? When you just put it in here, okay? And you can do your math correctly and come up with K. Right? Let's talk about LeChatelier. This is bread and cheese sandwiches. If you have bread and cheese together, they make sandwiches. Remember, this is a closed container. And LeChatelier says you can stress out a system by changing the concentration, the amount, by changing the pressure or the volume. Those are related. Remember, boil, okay? Or the temperature. All right? So let's go ahead and do concentration first. So I'm going to add N2. Physically, I'm giving you more bread. What can you do better? Oh, you can make sandwiches better. That means you're going to use up your cheese. The cheese is going to go down because what's going to happen? Bread and cheese are going to go together in this direction to make more sandwiches. So my sandwiches go up. And the shift is going to be in this direction. Okay? So this is the shift. And remember, yes, this does go up, but that's physically what I'm doing. I am changing that. I'm saying, what happens if I add N2? Let's try another one. What happens if I take this away? I'm going to take away the cheese. What's going to happen? Well, bread's freaking out. It says, hey, I need more cheese. Hey, sandwiches, break down. If you break sandwiches down, what are sandwiches made of? Bread and cheese. So if you take the bread away, the sandwiches are going to break down and replace the cheese, but they're also going to increase the amount of bread. So this goes up, and these are physically going down because they are breaking apart to replace the cheese that was removed, and the shift goes in this direction because you see a bunch of stuff going in that direction. Okay, if you want to think it's like a conveyor belt going back and forth here, right? Okay, back and forth. The bread and cheese combine to make sandwiches. The sandwiches break down to form bread and cheese. All right, let's do another one. Oops, sorry. Let's increase the pressure. Increasing pressure is all about, sorry, let me erase some of this. It's all about the moles. So if you look at this, how many moles do I have on this side? I have 4 total moles, right? 1 and 3 make 4. So on this side of my factory, I have 4 moles, and on this side, I have 2. What would happen if the walls of my factory closed in? The volume is decreasing, the walls are moving in, the pressure's going up. The moles are freaking out. They're going, whoa, what's going to happen? Okay, remember, this isn't just 4, it's like lots. It's a ratio. So if you have 40,000 moles on one side of a room, and there's a fence to jump over, and 20,000 on the other, I don't know about you, but I would physically see stuff going in this direction. So it's going to shift to the right. This side goes down, and this side goes up until everyone's happy and things have kind of recalibrated, and okay? Now, if the volume goes up and the pressure goes down, it's kind of weird. Because I'm going to stretch the walls of my room to Mars, to Jupiter. All of a sudden, these guys can go back in this direction. That might not make as much sense to you. So remember, it's the opposite at this point. All right, so let's get rid of that. So remember, if you have moles, it jumps from more to less. More moles on one side go to the less on the other. So let's actually do a different equation. I'll just make it x and y, okay? So here we go. X, I guess we should line it with the bread and cheese sandwiches, huh? Oops. So x is bread. Y is cheese. I have sandwiches over here. Let's make that Z. Let's make this an exothermic reaction. If it's exothermic, just go ahead and treat that word as heat. It was endo, heat would be on this side, wouldn't it? Right, this is exo, heat's exiting. This would be endo, so a different reaction. Okay, so let's do this. I'm only going to do it for one of them. I'm going to add heat. What happens when I add heat? Well, this side can break down better. Z can form Y and X. So Y is going to go up, and X is going to go up, and Z is going to go down. Now, that's going to happen permanently, and that changes the value of K. Okay, nothing changes the value of K except for temperature. And the shift goes in this direction. Okay, let's try this one. Let's take heat away. I'm going to remove heat. I'm going to make it cold. I'm going to remove heat. It's gone. Well, Z's freaking out. The sandwiches are going, whoa, it's getting cold on this side. Come on, bread and cheese. Oh. So these are going to go down to make more sandwiches. That's going to go up to replace this heat that's taken away. And the shift's going to be at the right. So 3 things that LeChatelier says: concentration, pressure, volume, temperature. Gas laws. This is the ideal gas law. PV equals nRT. Park view, not RT. Pressure, volume, moles, R. These are the values of R. Those are crazy labels. They're not an equation. And know that there's 2 different values for them. So let's do a problem. I have 20 degrees Celsius, 720 milliliters, 720 millimeters of mercury. Find the grams of oxygen. I need to choose. Well, I'm going to go ahead and choose this R. They're not going to give you both. So let's just say they give you the 0.0821. Okay? Get rid of this. Let me just say, though, that if you did have that one, you would have to change your pressure to kPa. And this one, you have to change it to atmospheres. That's why I like R. It tells me that when I have R, I need to change everything to be matchy-matchy and match that R label. So what do I have? I have 20 degrees Celsius. So I need to change 20 degrees Celsius to Kelvin. It's 293. All right, 720 milliliters. To change it to liters, I need to go 1, 2, 3. So it's 0.720 liters. To change millimeters of mercury to atmospheres, I need to go 720 millimeters of mercury to 760. Remember, our values, what are they? They are 1 atmosphere, 760 millimeters of mercury, 760 torr, and bad radio station, 101.3 kPa. So what's true? That's equal to 1 atmosphere. So when I do my math, I'm going to go ahead and find grams. That means I need to find moles. So I'm going to be smart and move my equation around to solve for moles. So plugging stuff in, I'm going ahead and put it in 0.947. That's what the answer to this is, right here. It's 0.947 atmospheres. 0.720 liters from up here. Right? R is R, 0.0821. They might give you 0.08206, but same thing. And then temperature, and temperature was 293. When I solve, I get, 0.283. I think that's right. Let's do that, so I'm going to give you the wrong math. 0.947 times 0.72. Sorry, thanks for bearing with me. 0.08. Okay, so make sure that you had the same math that I had. Now that is moles. And what do I want? I want grams of oxygen, genuine, Brinkelhoff, diatomic. 1 mole of oxygen is 32, right? So times 32, and the answer is 0.907 grams of O2. That's your answer. All right, combined gas law. You ever forget it, folks? All you do is solve for R. So I'm going to go ahead and divide by NT on both sides. Those go away. And looky, looky. I am left with P1 V1 over N1 T1. Remember, a lot of Chem 1 teachers don't teach you the N is there, but if you need it, there it is. Boyle is a relationship between volume and pressure. He's an indirect dude, so guess what? His relationship is this. What do you do with it? You cross that off, don't you? So you have this right here. Charles is the relationship between volume and temperature. So there's your equation. Gay-Lussac drives a Petit Cruiser, so there's your relationship. And you plug in and solve. Remember, temperature, you always have to change degrees Celsius to Kelvin by adding 273. Oh, the other thing I was going to tell you is this. If you have a combined gas law problem, so let's get rid of this, make the eraser big. Okay, I'm not going to do a problem, but let's just say I have 3 atmospheres, and it's 223 Kelvin and 5 liters. What's the new volume at STP? Well, what's STP? Everything you memorized. So we're going to plug in 3 for the atmospheres for P1. V1 is 5 liters, and this is 223 Kelvin. The only thing you need to worry about with combined is changing the temperature. The pressure and volume doesn't matter if it's in milliliters or kPa. As a matter of fact, let's change it. Let's change it on purpose here to kPa. Let's make it 301.5 kPa, just so you know. Okay? Now, what's true? Those are my P1, V1, T1. I'm going to change it to standard temperature. So what is the pressure? 101.3 kPa. I don't know the volume. And it's 273 down here, and you solve. Specific heat. Specific heat tells you that if I have something that has a low specific heat, it heats up easily. If it has a high specific heat, it takes a heck of a lot of energy to heat it up. Water, as you know, has that. The specific heat for water is 4.184 joules per gram degrees Celsius. If you can't remember that, remember 4.2. That's also equal to 1 calorie. Let's do this problem. I have 300 joules. They're used to heat water. I don't know how much water. This is my X. I'm heating it from 20 to 40 degrees. Find the mass. The equation for this is Q equals mc delta T. If you can't remember what that is, remember you have water. What do you have? You have a certain amount of energy. It's 300 joules. That's how much energy used to raise. I have no idea how much mass I have. Do you know how much of water you have? Like a teacup or a bathtub full? You need to know what, so that's the mass. This is what it is, specific heat. What's the specific heat for water? 4.184, or if you remember 4.2, that will work. Okay? That's the energy needed to raise 1 gram of water by 1 degree Celsius. What's the change in temperature? From 20 to 40, that's a 20 degrees Celsius. So if you look at this, I'm going to go ahead and solve. How do you solve? You divide both sides by 4.2 and 20. I'm going to write the units in here so you can see. Remember, this isn't gas law, so I don't change it. The only time I change Celsius is when I have gas laws. What's going on? So, joules cancel, Celsius cancels, and I have 1 over grams on the bottom, which is what this is when it works out math-wise. So if I do my math and divide, I'm going to get 3.82 grams. Now, what if What if they wanted to know the answer in calories? Let's say instead, sorry, I'm taking so long to erase here. Let's say instead I have 300 calories. So this is 300 calories equals, I have no idea how many grams. This is 1. Ooh, that's hard. 1 calorie. And it's 20 degrees here. So you solve 300 divided by 20. And that would be your answer. Okay? Excuse me. And your answer would be 15 calories. Okay? So you need to remember this. Alright, ice. I have ice. It's at 0 degrees. They could say that or not. You have 30 moles of it. That's a heck of a lot of ice. So, what do you know about ice? They tell you the heat of fusion. It's 6.02 joules per gram. Yep. Guess what? You have a discrepancy already, don't you? So you know you have 30 moles of ice. They want to know how much energy it takes to melt it, or how much is given off when it freezes. Melting, freezing, isn't that heat of fusion? Remember your heating cooling curve? Right? And I'm right here, aren't I? Okay? So 30 moles. So I need to change moles to grams. There's our handy dandy water, right? Okay? And so when I get that, I get 540.6 grams. That's how much ice you have. So think about it. You have 540.6 grams of ice, and it takes 6.02 joules per 1 gram. So I'm going to go ahead and say for every gram, it takes 6.02 joules. And that means my answer, when I multiply it, is 3254 joules needed. If you notice, the temperature's not changing, so you know you're not using specific heat. That's the same thing for heat of vaporization, right? This is fusion. So this is how much energy it would take to condense or to evaporate a liquid. And I think that's it for this podcast, guys. I need you to review and go over your lab safety, your lab equipment, percent error, all that stuff. Okay?